guys, in this tutorial we will go over the basics of logistic regression. Before we start, please, if you find value out of this tutorial, like and subscribe. Also, the links to the notes and the code that you will see in this tutorial can be found in the description box. That being said, let's get to it. Introduction to logistic regression. So logistic regression is one of those fundamental models that anyone who is interested in the machine learning or data science field needs to know. Okay, it's a very fundamental model. Okay, so one thing that I want to emphasize here is the following. So even though it has the regression label attached to the name, logistic regression is not a model for regression purposes, meaning that this model it wasn't developed to predict the number. Okay, on the other hand, it was a model that it was developed to classify observations. So then technically speaking, logistic regression is a classification model. Okay, so again, just pretty much ignore the regression label that you have in the name of the model. So logistic regression is a model for classification purposes. Okay. All right, so let's start with section 1, introduction to logistic regression. So logistic regression is a fundamental algorithm for binary classification problems. So anytime that you see or that you read binary classification, that typically refers to a 0-1 classification. Okay. However, logistic regression is not only restricted to 0-1 classification task. You can also use logistic regression in the case of multi-class classification problems, meaning that if you have 3 or more classes and then you're planning to, or the goal is to predict those classes, logistic regression can also be adapted to that scenario. Okay, so I don't want you to think that logistic regression only works in binary classification. No, in general, it works in any classification problems. It could be a binary classification, meaning that there are only 2 labels that we want to predict, or multi-class classification, meaning that we have 3 or more labels that we want to predict. Okay, so despite the name, it is a classification model that predicts the probability that a given input belongs to a particular category. So these models, the logistic regression model, estimate the likelihood that a given observations belongs to, in the case of binary classification, the likelihood that belongs to the 0 class and the likelihood that belongs to the 1 class. Okay. Now let's go over the mathematical foundation associated to the logistic regression model. So basically what this model is doing is estimating the probability that a given observation denoted by x belongs to class 1. That's basically what the modeling or what the logistic regression model is modeling. Okay, and it models that relationship by using the logistic function, and that is the reason why the model is called logistic regression. Okay, so then technically speaking, the model, it looks like this, right? So it looks like the probability of y is equal to 1 is, let me rewrite this. The probability that the y is equal to 1 given x divided by 1 minus the probability of y is equal to 1 given x is equal to e raised to the beta 0 plus beta 1 times x1 plus beta 2 times x2 plus dot 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 beta n times xn. Okay, so if you look at the left side of the equation, this is typically referred as the odds, right? Odds is just the ratio of the probability that the event happens divided by the probability that the event doesn't happen. Okay, so the logistic regression model basically is modeling the odds. Okay, and then we go from this expression right here. So we go from here into this particular formulation just by doing some basic algebraic manipulations. Okay, so here, right, what you have on the left side of the quality, so it's just a ratio. So then basically the quantity that you want to solve for is the probability that y is equal to 1 given x. So it becomes a one equation with one unknown. Okay, and also notice that here that we have the Euler number. Okay, so and then basically you can take the log on both sides and solve for x, and then at the end of the day, right, just by doing some basic algebraic manipulation, you arrive to this expression right here, that the probability of y is equal to 1 given x is equal to 1 divided by 1 plus e raised to the negative beta 0 plus beta 1 times x1 plus dot 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 beta n times xn. Okay, now at this point the goal is just, given the data that we have, right, is just to estimate the parameters beta 0, beta 1, beta n, because the moment that we have values for those parameters, at that point we can pretty much estimate the likelihood that a given observation belongs to class 1. Okay, so yes, at that point, once you have the model written in this particular form, right, it more or less looks like a traditional linear regression model, right? So then we have some parameters and we need to estimate those parameters, and when those parameters are estimated, then we can start generating predictions in some sense. Okay, all right, so let me go back here. Yes, so then the predicted output is interpreted as a probability, and the threshold is typically 50%. Is that gonna be the case all the time? Probably not. Depending on the context of the problem that you're working on, it is estimating the threshold is going to be another task. Okay, so 50% is the default value, but then again, that may not be the optimal threshold for your task at hand. Okay, so again, and then once you have estimated values for those parameters, then at that point you can estimate likelihoods. And that's basically, you know, the goal of logistic regression model. Okay, now let's move to the next section, which is application of logistic regression in data science. So logistic regression is a very old model, and is, again, as I mentioned before, is one of those fundamental models that anyone who is interested in the data science machine learning field needs to know. Okay, it's being applied on many different fields. Here I have a very short list of fields in which logistic regression is being applied. It's being applied in healthcare, marketing, finance, human resources, email filtering, and many other fields. In healthcare, it's being used as predicting a disease presence, whether whether you have a specific disease, which it could be diabetes, cancer, and others. In marketing, it's being widely applied in customer churn. So in finance, it's being applied in fraud detection, human resources, predicting employee attrition. Email filtering is just estimating the likelihood that a given email that in some sense make it to your inbox how likely that email is spam. Okay. Now let's briefly talk about the pros and the cons of logistic regression. So first, let's start with the pros. Logistic regression is very simple and interpretable. Okay. It is really fast to train. Okay. It works really well when the data is linearly separable, meaning that you can easily separate the two classes, assuming that you're working in a binary classification. It's easy to separate the two classes of interest. Okay, if that is the case, if you can easily separate the two classes, logistic regression will work really well in that scenario. Also, another advantage or another pro associated to logistic regression is you have that probabilistic output. Okay, however, this is not going to be a unique feature associated to logistic regression. Pretty much any classification model these days, they can they output the likelihoods associated to the label of interest. Okay, so then again, don't think that just a probabilistic output is a unique feature associated to logistic regression. No, that is not the case. You can have that, or you can extract that from pretty much any classification model these days. Now the cons associated to logistic regression. Number one is it assumes linearity, right? Just by looking at this, how the model looks like, right? Or we can look at this expression that I have here. So in some sense, it assumes that there is a linearity between the log of the odds and the input features, right? And the what I mean by the input features is x1, x2, all the way to xn. Now, that could be appropriate in some scenarios, but then that probably is not going to be the best assumptions in every single data set out there. Okay, so as I always mention, the world that we live in is complex and messy. So then if you assume that linearity is going to solve all the problems, that's probably an incorrect assumption. Okay, because again, in nature, most of the relationships out there in terms of, think in terms of data and variables, they are going to be very non-linear in nature. So then making a linearity assumption probably is not going to be ideal. All right, so then one big con is just it assumes linearity. Another one is it's not ideal for high dimensional sparse data. Okay, another con is very sensitive to outliers and multicollinearity. Okay, because it has the linearity assumption built in. Multicollinearity, it could cause a lot of issues, especially when it comes to estimating the betas in the logistic regression model. Okay. Another limitation or another con associated to the logistic regression model is can be limited in capturing complex patterns compared to tree-based models or neural networks. Again, that has to do with the linearity assumption, because not every single relationship out there is going to be linear in nature. So if the data happens to be non-linear, so using a logistic regression model probably is not going to help you to capture those relationships and exploit them just to make good predictions. Okay. The next section is when to use logistic regression. When the target variable is binary and categorical. And again, I don't want you to think that logistic regression can only be used in binary classification problems. The reality is that it could be used in any classification problem in general, right? Doesn't matter how many labels the target variable has. It could have 2 labels, or it could have 3 or more labels. Okay, so logistic regression will work. Okay. When another reason when you need to use logistic regression is when you need a fast interpretable baseline model. Okay, given that linearity assumption that is built in logistic regression, it could be easy, or it could be easier to understand and explain that model to others. Okay, and when the relationship between the features and the log odds is roughly linear. Okay, so then so then that goes back to the linearity assumption. Okay, and the last section that I have here is the summary. So logistic regression is an essential tool for any data scientist. It is simple, interpretable, and often performs surprisingly well on real-world binary classification problems. And again, it's not like logistic regression only works in binary classification, it works in any classification problem. Okay, understanding its assumptions, strengths, and limitation is crucial for building better models. Okay, and one last thing that I want to mention about logistic regression is assuming that you have lots and lots of data, it's really good at making generalizations. Okay, so if you have, let's say, millions and millions of rows of data, so logistic regression can be, and I've seen logistic regression being used as a stacker, is being used as a model ensembler in some sense to generalize the prediction of other models. So basically the takeaway message of logistic regression is don't overestimate, or don't underestimate logistic regression. Okay, it's a good model. However, it has some limitations like any other models. Okay, so yeah, so that's all I have in terms of the notes. Okay, in terms of the notes, now let's just jump into a very basic toy example that will highlight how you can build and evaluate a logistic regression model. Okay. All right, guys. Now we're going to I'm going to show you how you can build and evaluate a logistic regression model using scikit-learn. So let's get to it. So first, as usual, we're going to start by loading pandas. So import pandas as pd, and then here reading the CSV file, and then in this case we're going to read the CSV file called bank full. So that's a very well-known CSV file in the machine learning community. Okay, so I'm gonna use the df label for my data frame. So pd read CSV bank full .csv. Close here. Df head. Let me select the kernel. All right, so here we have, let me add some labels here. So reading the data. All right, so here we're reading the data as a CSV file, and it seems like something went wrong. The reason why we don't see the data as we would expect is the following, because in this particular data file, this is an old CSV file. The data delimiter is not a blank space. The data delimiter is a semicolon. Okay, so that's the reason why the data doesn't look as, in some sense, as normal. Okay, so we can easily fix that by doing step equals to semicolon in quotes. Okay, so this argument right here in pandas, it will allow you to specify what is the data delimiter, which in this case is a semicolon. All right, so again, just a quick description of the file. So this is data that comes from, I think is from an old bank in Europe, I believe it is. So we have some basic information on the customers of these banks. So we have age, job, marital status, education, whether at some point that that customer has default, the balance, housing, loan, etc. Okay, at the end of the day, what we are interested in is on predicting why. Okay, so this is just some basic demographic information associated to bank customers. And in this particular case, this was a marketing campaign that it was run on the bank customers just to see if they will subscribe to a specific, I think it was a specific direct deposit or something along those lines. Okay, so then the target variable in this case is y. So let's quickly look at that. So df y value counts. So yeah, so then we have two labels, no and yes. No, that means that the customer didn't subscribe to the automatic direct deposit, I think it is. And yes, it means that they actually subscribe to that. Okay, so if we want to, so yeah, just value counts, it shows raw numbers. And if we want to see percentages instead of raw numbers, we will use normalize equals to true, and that will show the data in terms of percentages. So then, roughly speaking, 88% of the data has a label no, and 11 or 12% has a label yes. Okay, so in machine learning, we refer to this type of data as an imbalanced data set. And the reason why we use the imbalanced data set label is because when one of the proportions associated to the one of the labels is much higher than the other label, so then that's when we refer to that data set as being imbalanced. Okay, why this is important? It is important when you are evaluating the model, meaning that when you are creating your cross-validation experiment, so as you're splitting your data to run your cross-validation experiment, you need to make sure that the proportions of zeros and ones, or in this case, the proportions of no and yes, more or less is the same across all the false. Okay, so that is the reason why this is, looking into these simple tables is important. Okay, so now what we're going to do is we're going to use all the information that we have from the customers right up to this point. So we're going to use all of those columns as predictor variables, and y is going to be our target variable. Okay, all right, so let's get to that. So defining input and target. So when it comes to defining an input and target in machine learning, it's very common to use X for inputs and Y for target. Okay, so and in this case, instead of using apply, what I'm going to use is map. Okay, so we're gonna be mapping. So we're gonna be mapping no to 0 and yes to 1. Okay, so map. Then here we need to enter a dictionary. So no is gonna be mapped to, let me use double quotes. No is gonna be mapped to 0. And yes is gonna be mapped to 1. Okay. All right, so up to that point, we have the input denoted by X and we have the output denoted by Y. So if we take a quick peek at X, so that's all of the data. And then if we take a quick peek at Y, now we don't see any more yes or no. Now we see zeros and ones. Okay. Now, one thing that I want to emphasize here is notice the sum of the variables. They are categorical variables, meaning that they store label information in them. So job, marital, education, default, housing, loan, and so on. Okay, so if we try to build a logistic regression model just the way the data is, so we will run into a bunch of error messages. So we need to pre-process those categorical variables before we actually build the model. And what I mean by processing those categorical variables, that means that we need to map the labels into numbers. Okay, so what we're going to do is the following. So let's say processing the input, that processing the input variables. So when it comes to doing the mapping from labels into numbers, it's very common to use the following. So from scikit-learn, pre-processing, import, we're gonna be importing, let's see, ordinal encoder. Okay, so let's use ordinal encoder. Okay, so in order to use ordinal encoder, so first we need to identify what are the variables that we want to map from labels into numbers. So what we do for that is we need to identify which of those are actually labels, right? So before we do that, again, one easy way to identify the variables in X that they are categorical, we just do that info. So we can see the job, marital, education, default, right? Housing, loan, contact, month, P outcome. So all of those are categorical data. So we need to identify, or we need to, yes, well, we already identify them, but then we need to map those into numbers. So one quick way to do that is the following. We can use this particular command. So then X select data types, and then in this case, the argument is include object. So it's going to grab all of those columns that has a data type equals to object. So it's going to only select those columns. So then if I add two lists here, let me print here categorical columns. So then it prints all of those variables: job, marital, education, default, housing, loan, content, month, and P outcome. So these are the variables that I want to map from labels into numbers. Okay, then after that, what we need to do is the following. So we need to define the ordinal encoder. So defining the ordinal encoder, so we can call it ordinal encoder parentheses, and that's what we load here. And then we just pretty much apply this. Okay, so we just apply the ordinal encoder, and then we apply the fit transform command on the columns, on the categorical columns. That's basically it. Okay, and then I run this, and then we can take a peek of that. And now we see that there is no more labels anymore. Now we have numbers. Okay, now everything is a number. Okay, so yeah, in here, right, this used to be X. We have labels here. Now after we apply the ordinal encoder, now we don't have any labels anymore. Okay, now everything is a number, and we need numbers in order to build a logistic regression model. Okay, all right, so we're almost there. So we have the data pretty much ready to go, and then let's run over 5-fold cross-validation experiment. So running 5-fold cross-validation. Okay, so then here, let's load the commands that we're gonna be using. So number one, let's, from scikit-learn, model selection, import cross-val score, stratify k-fold, then from scikit-learn linear model, import logistic regression. And one more thing that I want to, or two more things that I want to load is from scikit-learn pre-processing standard scalar, from scikit-learn pipeline make pipeline. So I think that's all we need. And then defining the cross-validation strategy. So I always like to use the SKF method or the SKF label. So stratify k-fold. All right. So stratify k-fold again, that has to do with creating the split of the data, right? And stratify will ensure that the proportion of zeros and ones in each of the folds are roughly speaking the same across all the folds. How many folds we're going to consider? 5. So here we are just shuffling the data before we split the data. And then this is just for reproducibility purposes. So 42 is the seed. Then after that, let's define the model. Defining the model. So I'm going to call it logic MD equals to make pipeline, standard scalar, and logistic regression. Let's ignore this for now. Let's use max iter 1000 and random state. Let's use 1, for example. It doesn't have to be 42 all the time. All right. The reason why I'm defining my model as a pipeline is because we're using logistic regression, or at least we're thinking about building a logistic regression model. Anytime that you are working or you are planning to build linear models, and that includes your traditional linear regression, lasso, ridge, elastic net, logistic regression, and in future tutorials we will talk about support vector machines, neural networks. All of those frameworks that are very, very sensitive to what data is fit into those. Meaning that if the input data happens to be on different ranges, so that's gonna have a negative effect, or most of the time it has a negative effect in the performance of the model. So just to make sure that we don't get into those issues, it's highly recommended to standardize the input data. And one way to do that is just by performing the standard scalar transformation on each of the columns. And that more or less will ensure that all of the input data are more or less on the same scale. So make pipeline is just another important command that you need to be aware of, especially if you're building machine learning models with scikit-learn. So this is just, so then the model will be built in 2 steps. First, you just standardize the input, and then it builds the model. Okay. So once the model is being defined, then we can run the cross-validation experiment. So running the cross-validation experiment. So I'm gonna call it logic CV equals to cross-val score. And you see, if you've been following along with my previous tutorials, that's another command that I use a lot just to run cross-validation experiments. So then the first argument is the model, so logic MD. Then after that is the input, after that is the target, then the cross-validation strategy, which is defined by CV. And then just to keep things simple, let's use the ROC AUC score. Okay, so the ROC AUC is one of those metrics that basically you can use to measure the performance of your classification model. If that's the best one, probably not. What I always recommend when it comes to evaluating models, always keep in mind how the model is going to be used. Okay, so if you're working on a real life projects, meaning that if you're building a model that is going to be used by a company, just ask questions in terms of how they are planning to use that model, and based on that you need to in some sense, based on that you need to identify what is the proper metric to evaluate the model. Okay, just in this case, just for illustration purposes, we're gonna be using the ROC AUC metric. Okay, and then we just print the results. So then print logistic regression AUC. Yeah, so let's run this. All right, so then the five-fold cross-validation ROC AUC score of the logistic regression model is 87% pretty much. The closer this number is to 1, the better, right? So then 1, having an ROC AUC score equal to 1, so then that means that you have a perfect model. But we know that such a thing doesn't exist. So then the closer that score is to 1, the better. Okay, so yeah, so then that's basically what I have for this toy example. Again, what I want to highlight here is a couple of things. Number one is when you're building logistic regression models, number one is all the input data has to be numerical. So then you need to make sure that you do some pre-processing in the case that you have categorical variables as inputs. Okay, and then the second thing is ensure that all of the input columns or all of the input features are more or less on the same scale. So then that way you get, in some sense, you get stable results. Okay, all right, so that's all I have for this tutorial. Again, logistic regression is one of those fundamental algorithms or fundamental models that if you're part of the data science, machine learning, and AI community, that you need to know. Okay, so once again, if you find value out of this video, like and subscribe. Yeah, that's all I have. See you on the next one.